Okay, so we are going to do, if this will go away, we're going to do 11.4. That is my marker that's dying that I need to throw away. I was just saying how this 11.4 is very simple. If anything, it's just kind of annoying because when you do a sample space of all these different outcomes, like there's like 36 of them one time. And so you literally have to write all 36. On the homework, you select between these different options. It's best to have it written down so when you look at the homework, you pick the right one. But like that's really the only thing that's like hard per se. Okay, so we have this one definition and it is sample space. A sample space is a list of all possible outcomes of an experiment. And then I just put in parentheses EXP because I think we say experiment like 3, 4, 5 times, and I'm just lazy. Okay, so within a sample space, we have what's called sample points. And so I'm just going to add to this sentence that we just wrote. Each outcome is called a sample point. So you perform an experiment and you have all these different possible outcomes that could happen. Each individual outcome, they're called sample points. A list of all sample points, which is all the outcomes, is called a sample space. So space is larger. It's actually made up of all the points. Points are just each individual little outcome within a whole sample space. Okay, so we have this principle that you pretty much use at the beginning of like every problem on the homework. It's called the fundamental counting principle. And the wording might seem weird, but the math that it takes to start these problems is very, very, very simple, okay? So if a first experiment can be performed in M, like a capital M, like for moon, in M ways, and a second experiment in N, like number, in N ways, then we use M times N to determine the total number of ways. Finally, they said the AC wasn't working, and I was like, well, we're gonna have class outside. Believe me, I would. There's a breeze out there. Y'all, we totally could. We could probably have class wherever we wanted to. It's just us. Then we use M times N to determine the total number of ways. Okay, so we literally have one little example of this. I don't remember exactly. There might be 2 or 3. So you're literally just going to see how many ways can the first experiment happen. That's your M. How many ways can the second experiment happen? Technically, y'all, it's like it's a sequence of events that happens, right? And we have an example like this. Well, no, let me give you one that we don't have written down. You go to a restaurant and like the first experiment or the first occurrence, the first sequence in this process is like selecting your appetizer, and there's 5 of them, right? And then after you select one appetizer, you select from the 15 entrees. Okay, so M is your 5. The second experiment, that's your entrees, and you do 5 times 15. That's your answer. So you literally just take the 2 numbers they give you and you multiply them together. Okay, and that's going to be how you actually figure out your sample points, which makes up every single outcome in your sample space. Okay, so example, and it's only the one, so I didn't number it. Okay, so first EXP, first experiment, can happen in 3 ways, comma, second experiment can happen in 5 ways. You'll see the word distinct in the problems, and I don't want it to confuse anybody, but whatever you get for the number of sample points, which is all of your outcomes, each individual one, like there's not there's some, but whenever you do this multiplication, that ends up being distinct ways that it could happen. So here, for the 3 ways, for the first experiment, that's my M. Second experiment, that's my N. If you have 3 appetizers and 5 entrees, there are 15 distinct ways that you could combine appetizers with entrees. Does that make sense? Okay. You can only pick one, and out of fried pickles, cheese sticks, and chips, right? And then you have 5 different entrees that you can pick. So if you actually go through there and you kind of pair these up together and you see all the number of outcomes, you'll end up getting 15. And that's just what this is saying. If you multiply your first number that they give you with the second number they give you, what you get is 15. In the wordy problems, you kind of have to think how many ways can the first thing happen and how many ways can the second thing happen, but it's the same thing. That is how you get all the total number of outcomes. Does that make sense? So if you see something and it talks about experiments occurring or happening 9 ways and then 6 ways, 9 times 6, your answer is 54. And then you kind of just move on, okay? And I know for a fact there's a handful of those. Oh, Tia, you want to come and grab these? Or Mario, you come and grab them for y'all? Just one of each. Like the last problem we use will be something, just one of each, just like that. There you go. Thank you so much. Okay, so I'm gonna do like the directions for the next 3 problems, and those are the only 3 problems we have that kind of wrap up 11.4, okay? Okay, so our directions are to determine the number of sample points, create a tree diagram, list the sample space, and determine the probability for the following. We could kind of label these like whenever we've determined the number of sample points, like that can be our A, our tree diagram can be our B. When we list the sample space, that could be C, and then determine the probability. We might do that a couple of times, but determining the probability, that'll be our D. I did just notice I didn't really do A, B, C, D parts for every problem, and it might help just to kind of keep it broken up. Okay, so first problem. It says a bowl, like a cereal bowl, right? Kind of, they say it's like a fish bowl. And this fish bowl has all these cards inside of it. And you're going to actually reach in and you're going to grab these cards out, okay? So a bowl contains 4 cards. A dog. It's weird to say it's a dog card, but apparently there's just these playing cards, I guess, that have a dog on one of them. We have a cat on another. If you notice, after dog in parentheses, I did a capital D. After cat in parentheses, I did a capital C. When we create our tree diagrams, you don't want to write the whole entire word of each individual thing. You'll see why, but just know you don't want to do that. Like, shorten it. Declare some capital letter for whatever it is they're talking about. In the homework, they should get a letter, okay? So we have a dog, we have a cat, we have a square, and a triangle. If you notice, each card began like with a different letter. You want to make sure that happens as well. Okay, so if you randomly select 2 cards, find the probability of selecting at least 1 square, comma. So it's like each comma is like a different probability, okay? We all know in the homework that would be like probability of this, the probability of that, probability. Right now, these are all individual probabilities. Find the probability of selecting at least 1 square, okay? We're gonna find the probability of selecting 2 dogs. And we're also gonna have a third example where we find the probability of 1 square, 2 dogs, and not a cat. When we get to part D, I'll actually do like it's P of, okay? And it'll look a lot like 1.4. They do use a little bit of the stuff that we did at 1.4 at the end of these problems, okay? So we kind of know our A, B, and C. I feel like I need to break up this monotony. That blue's a lot thinner than I thought it was gonna be. Oh, here's a blue. Okay, so for part A, it is the sample points, okay? Our sample points are found. Can y'all actually see that? Is that gonna be okay if I keep that, or do you want me to change? Is that one okay? It's like real light, right? I have like I should have my purple in here. Ooh, this one's like a sea foam. Do I not have purple? Okay, we'll see. This one should be good. It's basically a green. The sample points are found out from doing our fundamental counting principle. Okay, so when you think about the first experiment that you perform, it's reaching into this fish bowl and grabbing a card. How many cards are there? We have the 4, right? Dog, cat, square, and triangle. So with the first experiment, it can happen 4 different times, right? Because there's 4 cards. We're assuming we put the card back, right? And then we reach back into it to draw our second card. And with the second experiment, there are also 4 cards. So this right here, that's my M, that's my N. Okay, if you do M times N, which is 4 times 4, you get that there are 16 sample points. Another way of saying this is that there's 16 total outcomes. And whenever we do the tree diagram, you should visually be able to see all the different outcomes, okay? So because it said that I selected 2 cards, the first experiment is selecting that first card. The second experiment is selecting that second card. And each time there was 4 cards. 4 times 4, 16. Okay? For part B, it said to draw a tree diagram. These greens aren't actually great. Let me see what this orange looks like. And then I'll probably just stick to my black if I need to. Oh yeah, no. It like blends in with the off-white cream paper. I'm just gonna stick to black. I don't have to question black. Okay, tree diagram. So you'll notice my math lab, it doesn't have you create these tree diagrams. I would recommend having it on your paper, and then what you do is they're going to give you all these options. You select the correct one, okay? And this is how it looks. This first set of branches is going to be our first experiment. Okay, so kind of like right there. This is our first experiment. This is the first time I reached into that fishbowl. Okay, and the 4 different options of cards that I had the ability to select were dog, cat, square, triangle, right? Now, whenever I perform the second experiment, which is reaching in that second time, I also had 4 different cards that I could be selecting from. What you do is say that you did select a dog. The very first card that you selected was a dog. It's gonna be hard to cover that up. Okay. Now, after I select this dog and I perform the first experiment, and then I reach back in, right? I could select a dog, a cat, a square, or a triangle. So off of this dog, we have 4 little branches that look like this. Okay. First experiment, I got a dog, and then I drew again, I got another dog. Or I could get a cat, or I could get a square, or I could get a triangle. And guess what? Say the first card that I drew was a cat. The second one, I still have 4 different possible outcomes. And it kind of sucks because they kind of start to overlap each other, but dog, cat, square, triangle, dog, cat, square, triangle. First time I reach in, I get a cat. Second time I reach in, it's any of the 4 cards. Does that make sense? First time I reach in, I get a square. Second time I reach in, it can be any of the 4. It doesn't change. And then lastly, if I reach in and the first card that I get is a triangle, that second time that I reach into this fishbowl, I did an S. I'm gonna get my thing. It doesn't really change much, but I don't want it. Second time I reach in, I could get a dog, I could get a cat, I could get a square, or I could get a triangle. Now there's kind of a way to test yourself here and see. Right? So that the first, these 4 first branches, that's your first experiment. And then all these little branches that go off of the first experiment, those are all what make up your second experiment. And there's a way to check yourself and see, hey, is this the correct tree diagram? Okay, so I knew that the first time I had 4 options, and then the second time they each had 4 options. But how many total did I say there were? 16. There's 16 total what? Sample points, which were what? All the outcomes. And look at this. If you go through here, this is 1 outcome, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All of these very, very, very last letters at the end of all the branches total up to 16. So that's going to be your tree diagram. What we need to do for C is let's list all of the outcomes. So C, when you list all of your outcomes, what you're doing is you're creating a sample space. And it's kind of like you just work your way like this. That first, not saying it's the first thing you're going to draw, but the first outcome that we have on our tree diagram is that you could draw a dog and then draw another dog. Okay, so the way you put this in your sample space is capital D, capital D. Here is an outcome, dog, dog. And then the next outcome,
11:13 a.m.
Thank you, Siri, for telling me what time it was. The second outcome is what? Dog, cat. And then dog square. And then dog triangle. And then cat dog. And then cat cat. And then cat square. And then cat triangle. You're going to put all of them together. So you go like DD, DC, DS, DT. CD, CC, CS, CT. SD, right? You're going to list all of them. Whenever we get done, we should have 16 different possible outcomes. So the second one is DC. Third is DS, and then DT. And then we have where the first card was a cat, and the second one was all of the other four. And then got a little smushed at the end. To my knowledge, on my math lab, I don't think they'll have you type this up and put commas in between and be like that tedious. Again, though, as always, I would have it written down so you have like a visual representation of what your tree diagram looks like and what your sample space looks like. You need to know how to create a tree diagram and a sample space, obviously, for the test. But you're going to select out of like 4 options which diagram is the one to that's correct. And then I also think you're going to select out of like A, B, C parts which one's the correct sample space, okay? But y'all need to know obviously how to like create that on your own, okay? So for D, we're going to find our probabilities. The first probability that we were given, find the probability of selecting at least one square. So probability of, right? P, and then open parentheses, probability of at least one square. What capital letter represents the square cards? The S, right? How many times do you, within your sample space, see that you at least drew one square? Did I draw a square here? At DD, dog, dog? No. Dog, cat? No. Dog square? Yes, that's at least one square, right? So I'm going to keep my finger here. There's no S, no S, no S, at least one S, no S, at least one S, at least one. There's 2, but that's okay. That's at least 1. I'm at 5 right now, right? And then this is 7, and then 8. 1, 2, 3, 4, 5, 6, 7. I thought I counted wrong, so I just wanted to double check. But does it make sense that the probability of selecting at least one square, I look at my sample space, when does selecting at least one square occur, right? How many times does that occur? That's like your favorable. The favorable is, what are they talking about? They're talking about selecting one square. That occurs 7 times over the total. What's my total number of outcomes? 16. That's your answer. Now, if it's a fraction that can be reduced, it will want you to reduce it. Obviously, it might be like, hey, your answer, even though it's correct, you know what I mean? Like, it's just not in the correct form. Does that make sense? Okay, because this right here is pretty much what the whole entire homework is. Okay, the first thing is just to kind of explain, you figure out the total number of ways or the total number of outcomes by doing this math right here. Once you do that, select the correct diagram, select the correct sample space, and then you compute the probability on your own, okay? So that was the first probability. Our second probability that we were asked to find was the probability of selecting 2 dogs. I reach into this fish bowl that has cards 2 times. What's the probability that what I end up selecting when I'm done, performing these experiments is dog, dog? How many times does that occur? Mario, was that your answer? Yeah. I saw his finger, I couldn't tell. Okay, here, that doesn't even have a dog. Doesn't even have a dog, no dog. That's a dog, but it's only 1. So that's not what they're looking for, right? Favorable. What are they talking about? The only time that I reach in there and get a dog and reach back in there and get another dog is 1 outcome out of how many? 16. Okay, 2 dogs would be DD, which happens 1 time out of 16 total. 1 is prime, therefore that can't be reduced any further. Okay, we had that last one, which I'm going to kind of have to smush here. It was the probability of not a cat. It's a probability. I know it's going to be favorable over total, so I went ahead and just put the 16 there, right? Favorable is, what are they talking about? They're talking about any outcome that does not include a C, that does not include a cat. So I could just count them. 1, I don't count DC, there's a cat in there, right? 1, 2, 3, none of those. 4, 5, 6, 7, 8, 9. 9 over 16. 9 is not prime, it's divisible by 3, 16 is not, 16 is even, 9 is not. That should be completely reduced, and that would be your answer. Does that make sense? Okay. That's the epitome of 11.4 right there. Don't get me wrong, we're going to do one more example that is very similar to this, and then we're going to talk about rolling 2 dice or 2 die. Actually, rolling 1 dice twice, or die. I hate saying die. I'm just going to say dice. You always have to deal with it. Which is just like this, but the sample space ends up being significantly larger. And that's why I gave y'all that piece of paper. And then that was it. Okay? So if everyone has that written down, I'm going to go and change pages. And y'all are welcome to keep these. I know I've said it before, but if anyone needs those, just take them. Okay. So we're still doing the same. I'm going to keep this just to make sure I don't mess up my ABCD. The same, find the sample points, create a tree diagram, list the sample space, determine the probability. It still has not changed, okay? Here's our example. It is our second example, and you are remodeling your bathroom. We just finished remodeling our kitchen and we're fixing to start on our bathroom. I definitely am going to end up having way more choices than this example, but it's good to know if I wanted to do the math on it, I could. You're remodeling your bathroom. You have the following. If you wanted to add paint colors, you can. I just did colors. You have the following colors to choose from. To paint your walls and trim. So, the following colors that we have for our walls are burgundy, Americano, and Frappe. And then for our trim, the following colors that we have to choose from are eggshell, powder, snow, and cotton. I literally had to Google other paint names for white paints because I was like, white and off-white. Like, I didn't know what to put. And I was like, oh, I'm gonna sound very creative now. So A, B, C, D, right? A is figuring out the sample points. We figure out our sample points by using the fundamental counting principle. Okay, you're gonna select one wall paint and one trim paint, right? So how many ways, right, how many M ways do I have to select a wall paint? How many different options are there? Yes, class, there's 3. And then for my trim, right, that's the second experiment, right? I'm gonna select one color for my trim out of how many colors? 4. There are a total number of 12, right? 3 times 4 distinct ways that I can combine these wall colors with these trim colors. I don't know if that made it better or not, but 12. For part B, tree diagram. Got 3 colors for that first experiment. View it as an experiment, and there's 3 different ways it can be performed. You go ahead, I definitely would never write burgundy, Americano, and frappe because you got to write it every single time. Eventually you're going to start shortening them to B, A, and F, so just go and short them now, right? Like that. That's that first experiment, right? Because I pick my wall paint. Then the second experiment, after I pick my wall paint, I'm going to pick one trim color. And I've got 4 of them. So I'm going to have 1, 2, 3, 4 little baby branches off of my A. I'm sorry, off of my B, my A, and my F. And those are eggshell, powder, snow, and cotton. So what? E, P, S, C? And then again, like I said, a good way to check yourself, is my tree diagram correct? Well, I know that the very last value, or the very last thing on all the end of my branches should total to the sample points. And if I look, I've got 1, 2, 3, 4, 12. So, okay, good. I didn't leave anything off. I didn't accidentally double up anywhere. I do have 12 things. This is essentially the list visually of all the different outcomes, and that is how you create your sample space. And that is C. I kind of just put C right here. I don't know why I went to the side, but maybe to be able to do my probabilities. My sample space, what is sample space? Page 1 definition said that a sample space is a list of all outcomes, right? And so what you do is you start, I just start on the left. I don't know if it's customary, but it's just where I start. I start with selecting burgundy, and then after that selecting eggshell. And then another outcome is burgundy and powder, and then burgundy and snow, and then burgundy and cotton. And then I notice I've ran out of all of those. I scooch over to here and I've got AE, AP, AS, AC. And then I have FE, FP, FS, and FC. If you notice, I have 3 rows and 4 columns, which, you know, if you did that, it's like a multiplication table. You're also going to get 12. You've listed them all correctly. You didn't double up anywhere. You didn't leave anything off. Okay. If you can do a square on your paper, sometimes it is a little bit easier. I have a hard time keeping things straight, but if you just have like a long run on, you know, like, and then you got to count them, like, it could just be annoying. Oh. Okay, so that was C. Now D, determine the probability. So for D, I only have 3 different probabilities. It's very similar to before, okay? You notice the wording changes because it's paint and it's not cat, dog, triangle, square. Cat, dog. I used to love that show. Okay, let's find the probability. You select Americano. Probability of Americano. Probability, fraction, denominator is the total, right? And then let me look. Favorable. Favorable means, what are they talking about? They're talking about Americano. Whether you look here or you look here, how many times does an outcome result in you having chosen Americano? Just here. It was the first experiment, so it has to occur right here underneath my Americano, and that actually has 1, 2, 3, 4 outcomes. If you write 4 over 12, it reduces to 1/3. And that's your answer. Okay, what about the probability? You choose Americano and cotton. So the probability that you choose Americano and cotton. Americano, I know that to be my wall color, which occurred in that first experiment. So I know I'm here. It says and cotton. Well, right here. Americano cotton is the only time Americano cotton happens. And that only occurs how many times? Literally 1 time, right? And so probability, fraction, denominator is the total. Favorable is 1. 1 is prime, which means it cannot be reduced. Okay. What about the probability? You do not choose frappe. Frappe. Is that how you say it? Frappe? Frappe? Frappuccino? I don't know. I'm done. Probability not frappe. Probability, fraction, denominator, total. Personally, I like this a little bit better. I don't know why, I just do. If it says not frappe, you want every single outcome that does not have a capital F in it, right? I've got 1, 2, 3, 4. I've got 5, 6, 7, 8. These 4, when you start with the F, are the only times that you have an outcome with an F. So it's the other 8 that are you not choosing frappe for your color of your walls. And if you reduce that, you get 2/3. Now, sometimes you might see this. If you don't see what I'm fixing to say, it's okay. If you read the words and it just really, really makes sense what it's asking, this is saying the probability of Americano. Americano only exists in this first experiment, right? So the probability of selecting Americano is only here. There's 3 total. I took away 2, so it's 1/3. And then the probability of not choosing frappe, out of these 3 predominant branches, I took away 1, so what's left is 2/3. Right? Doing it all the exact same way in every step is not a problem, but you could see something like that. Just make it a little bit easier to answer it a little bit quicker. Okay, y'all, so let's look at our last example. Do you see how it's just tedious? Each little individual thing's not hard. Kind of similar to the 11.1. Look at this. And if I see more formulas, which I think we will in chapter 12, like mean, median, and mode, like to figure those out, what I'll do is I'll just kind of scoot these around and put those formulas there, and it'll be something that, like, you can use this on the test, obviously, okay? I'm not going to expect y'all to remember or have to memorize this. But what's on the bottom is what's new for us right now. These are essentially the table of outcomes when you roll 2 dice, or if you roll a dice twice, right? So like this first column would be like the outcomes of your first roll. This first row would be like the outcomes of your second roll. And if you look at this row with the 1 and then this column with the 1, they kind of put it together as like a coordinated pair. And so it's just saying that that roll resulted in a 1-1. Having this in front of you, it just keeps you from having to list out the sample space, okay? The dice to the right is the exact same thing, but instead of it showing you the number of the dots, it actually shows you the way it looks on the dice with the dots. But there's nothing different in these. Okay. So let's do this third example. This is all it says. A single fair die is rolled twice. We have A, B, C, D, E, F parts. C, D, E, F are all just a probability. They could almost be paired together, but they're not. Not on this homework example. Okay. So a single fair die, it's rolled twice. So the first experiment is the first roll. The second experiment is the second roll. Okay, so it tells me to determine the total number of sample points, and this is pretty circular, but sample points are all of the outcomes in a sample space, and a sample space is just a list of all of the outcomes. If you look at this piece of paper, this is a dice that, is being rolled twice. In the first experiment, we have 6 possibilities, or like it could happen 6 times. And with the second dice or the second roll, it also can happen 6 times. And so that's our M and our M. I'm stuttering because it's very not natural to say rolling a dice 1 time. That experiment can be performed 6 times, or there's 6, in my mind it's like there's 6 different outcomes. You can roll a 1, you can roll a 2, 3, 4, 5, or a 6, right? These are the possible outcomes, so that's your M. When you roll the dice again, you still have 6 different things that you can roll. That's your N, and that's what totals it 36. But as a cheat, I've done this. Y'all, if you did like a multiplication table, 6 rows times 6 columns is 36. Okay, or you go through there and count them 1, 2, 3, 4, 5, 6, and you'll get 36. Okay, tree diagram. Okay, this one's annoying, but it just is what it is. I'm going to turn my page, and I'm going to go like 1, 2, I could have made them way shorter. I think I actually am going to make them a little bit shorter. But if you notice, I did 6 branches. And this is what? The first, like, predominant branches that start my tree diagram. That's my first experiment. Okay? And whenever I perform the first experiment, I have the 6 different possible outcomes, which are 1, 2, 3, 4, 5, and 6. So I'm literally going to write them under here. 1, 2, 3, 4, 5, and 6. This one is just bound to get messy and clumped together, but it is what it is. This is the first experiment I rolled. These were my 6 possible outcomes, which is why I have my 6 here. Whenever I pick the dice up and I roll it again, I also have 6 outcomes. So on my 1, I need to have 6 little baby branches. So again, it gets cluttery, okay? So I'm just gonna kind of turn 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Then we have 1, 2, 3. If and when you do this problem on the homework, there is, I think, 2 dice problems, I want to say. I really don't remember. They don't make you create this, they make you select the correct one. So even if it says it's being rolled twice, y'all just pick up your notes from today and look so you have it in front of you, okay? For C, what we're going to do is go ahead and create our sample space. A sample space is made up of all the sample points, which is just a list of all the possible outcomes. And so I did it like this. I just did 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. Those are all the outcomes if I roll a 1 first, and then I paired it with all the different outcomes for the second experiment. And then what else would I have? 2, 1. 1, 2, 2. And 2, 3. Y'all have noticed a pattern, so I'm just kind of filling it in that way. Okay, did that. And it's literally right here, but we're just completing the problem, okay, as if we didn't have this in front of us. Okay, so this is the total number of sample points, which makes up the total number of outcomes, which is evident by the tree diagram, because if I went through and I counted all of these, I would actually get 36 total. Sample space is just a list of every single outcome. And then for D, we're going to find the probability of, we're just going to dot it. And then we're just going to have 1, 2, 3, 4 different ones. I kind of just did little bullets. Okay, Okay, so if I roll a single fair die twice, what is the probability of rolling a double? A double literally meaning that you have the same number twice. And so whenever I would start looking for the outcomes that they're asking me about to find the probability, I'd always just start 1, 1, pretty much every single time. 1, 1, isn't that a double? Right? 1 and 1, double numbers. What happens if I go like that? 2, 2, isn't that a double? And then what else? And then what else? And then what else? And then what else? You notice how it's kind of crazy? It's actually kind of beautiful in some other classes. Like you'll notice that a lot of these things happen on like a diagonal kind of, you know? There is 1, 2, 3, 4, 5, 6 favorable outcomes, what they're talking about, over how many total? 36, right? 6 goes into 6 one time. 6 goes into 36 6 times. 1/6. And because everything reduces, you essentially could just, well, for this example, I don't know if that follows all the way through, like the cards. I don't want to say anything. Okay, let's find this one. What is the probability that when you roll these 2 rolls, what you end up getting is a sum of 10? Probability, fraction, denominators, total. I can go ahead and do that right now, right? And then what sums to 10? On this row with my first roll being 1, never does it happen. First row being 2, never does it happen. 3, never does it happen. 4, yes. At 4 plus 6, that would be 10. And then when I go on the row of 5s, I get 5 plus 5. And then I get 6 plus 4. Do you see how that kind of went on a diagonal too? There are 3 times favorable to this probability. And if you reduce that, you get 1/12. What about the probability that when I roll this die twice, I get a sum of 6? I'm going to find the first one that sums to 6, which is right here at 1 plus 5. I've noticed that things happen on a diagonal, so I'm just going to play around with that. And if I go like this to 2.4, that sums to 6, right? What did I say, 2.4? To 2 and 4, that sums to 6. What about 3, 3? And 4, 2? And 5, 1? Do you see how there's 5 total outcomes where they all sum to 6? 5 is the favorable, 36 is the total, 5 is prime, therefore it cannot be reduced any further. And then lastly, not lastly, I have one more, sorry, I just saw it. What if whenever you roll 2 times, you get a sum of 12? Probability is a fraction. Your denominator is the total number of outcomes, which is 36. How many times does rolling a 1 happen? 1. I basically just give you the answer. How many times does rolling a sum of 12 happen? It's just 1 time, right? It's 6 and 6. No. Probably sum of 12, 1 over 36. That was it. That was it. I don't know when I looked up, I don't know what I saw, but I thought it was a whole other example.